So, welcome back once again, and we are going to talk about a new chapter, Magnetism and Matter. Okay, and I will not waste your time much. It's stated that about 600 BC, 2600 years before, in an island called Magnesia in the then Greece, this had something called lodestone or lodestone. Okay, and from there it had strange properties, unique properties associated with that, and when the bars were cut out of it, and they showed very striking properties. Okay, one of the things that we know is that the earth is also a magnet, with the magnetic field pointing to the nearly the geographical north pole from the geographical south pole. Okay, although the geographical north pole and the magnetic north poles are a bit different places, there is an inclination, etc. We'll talk about in the due course of time. The earth acts as a magnet. It has got a magnetic field which maps the whole of the earth, and at different points on the surface of the earth there are different values of the magnetic field. Okay. One of the ends, if we suspend a bar magnet freely or put it on a cork in still water, then the bar magnet, it clearly shows that it has a north pole and a south pole. We can say north pole from south pole, etc. So for example, if the bar magnet is like this, if this is north then this is south, but if this is north then this is south. Okay, in the opposite, to the opposite ends. Okay. Another property is that if we have two magnets with defined north and defined south, and we bring north and south and south together, then there is a repulsion. Else, if a north is brought towards south or south is brought towards north, oh, there is a kind of an attraction. They like each other. Okay. No isolation of north pole or south pole is possible. Okay, that means they have to occur in pairs. Like for example, if there is a long bar magnet with uniform area of cross section, and we want to see and check an experiment as to what happens if we cut it somewhere in the middle and make it two pieces. Those pieces could be equal in length or unequal, doesn't matter. What happens is that one piece has a north and south like this, the other piece has a north and south like this, their strengths are reduced. Okay, but the pair, like here, remains the same. They function like this one. Okay. Sometimes what we can do is that we can cut it from the middle. Okay, like this for example. If we cut it from the middle, somewhere, I mean, they need not be equal in size, they can be unequal, but we again have the north-south, and the strength is reduced, like that. We can talk about that. So, what I mean by saying this point, that magnetic monopoles do not and cannot exist like the electric monopoles, positive charge and negative charge, they can be separated, they can exist all by themselves, but the magnets cannot exist all by themselves. Generally, magnets are made of iron and its alloys, but there are many materials out of which we can make magnets. Okay. In a magnetic field, all materials and tiny particles over there, they make one kind or the other kind of magnetism. There are ferromagnets, ferrimagnets, okay, this magnet, that magnet, so many kinds of materials are there. Paramagnetism, ferromagnetism, ferrimagnetism, etc., etc. We will talk about that when the occasion comes. Okay. Now, I have deliberately not included the magnetic field lines associated with a bar magnet or a solenoid, etc. Okay. Because it's not possible for me to draw them here and show it to you. And I suggest that you do open your textbooks or help books, and there they take pride in trying to explain you the magnetic lines of field which are obtained by the filings of iron, and you put the filings of iron and then tap there, and they will make a beautiful pattern, the lines of field. When we study that, and similarly the field lines are obtained also in the case of the electric dipole and electric monopoles, etc. But there is a difference, and the difference is that magnetic field lines, we also used to call that magnetic lines of force long back, but we had abandoned that because they are field lines. After all, when the field concept was clear to us, we talked, and since then we have been talking about magnetic field lines. And magnetic field lines are continuous, not broken, continuous, closed loops. That's not the case in the case of electric field lines, electrostatic field lines, etc. Of course, the second property, that the tangent drawn to a field line is in the direction of net value of P. Okay, so it is tangential to wherever it is. You will understand that easily in the due course of time. Number 3, and this also I told you in the case of the lines of field associated with charges, that the magnitude of the field, magnetic field, this is proportional to the number of lines crossing a unit area. Okay, that means if there is a unit area which we take normal, okay, to a set of lines which is crossing that over here and then again here, then we see that the number of lines of field which are going through this, okay, is more, and the lines are very close to each other, where we have, and we are going to talk about what is the larger strength of the magnetic field. Where the strength of magnetic field is less, there the number of lines which crosses, which crosses the unit area, that becomes less. Okay, so the density of lines of field indicates the strength of the magnetic field. Well, the fourth property of the magnetic field lines is also similar to the properties of electric field lines, and that is field lines do not intersect. No, this kind of an intersection is illegal, because if you say that one field line goes like this and another field line comes like this, that means at this point there are two values, whereas they do not cross, they do not intersect, because each of them has a unique value. Okay. With that little bit of introduction to you, and with my suggestion that you look into the book for the lines of field which are drawn in the books, okay, by artists, or they can be obtained by taking the photograph, etc., in some beautiful books, okay, particularly the American ones. But I don't need to draw any conclusions from there, and I leave it to you to draw your own conclusions. The next item which I am going to talk about is the bar magnet and the solenoid compared to each other. So let's talk about and discuss a bar magnet as an equivalent solenoid. Okay. So I take a solenoid of length L plus L, which is 2L, and I'm just taking a representative term of the wire on the solenoid, okay, and I take the middle of the solenoid over here, from where I measure the distance R on the axis of this solenoid. Okay, the radius of the solenoid is A. Okay, the cylindrical radius of the solenoid is A. This total length is equal to 2L. Okay, and the magnetic field is shown over here to be going inside the plane of the board. Okay, now let's define a few things. As we know that this is the magnetic dipole moment associated with the system, which is equal to the total number of turns N into I into A, where A is vector, area vector, okay, surface area vector. Now let's take N as a number of turns per unit length on the solenoid. So let's write for this one, for example, this loop over here, and dB, which will be like this into the board, and the dB will turn out to be equal to like mu naught n dx, that is the total length, total number of turns, okay, n into dx, in the element dx, length dx, into I, the current in the solenoid, into the area, okay, NIA, this, and we find that at a length like this we'll obtain this value as divided by 2 pi r minus x. This is r and this is x, okay, r minus x whole square plus a square total raised to the power of 3 by 2, and that takes care of the cosine theta factor as well. Okay, so I can write this, assimilate this as follows, that I'll cancel the pi with pi, and I'll get mu naught n I a square upon 2 r minus x whole square plus a square raised to the power 3 by 2 into dx. Okay, so when I add all these due to the various dB elements, that means we integrate it, and because the variable over here is dx, so mu naught nia square upon 2, this will turn out to be a constant which I can take outside the integral, and the integral is carried out within the limits minus L to L. This is minus L, this is L. Okay. R minus x whole square plus a square raised to the power of 3 by 2 dx. Okay. But it's difficult to do, but we can make our life safer if we take that if R is very, very large as compared to A on the axis far away from the center of the solenoid. Okay, then R is very, very large as compared to A, and also we take R as very, very large as compared to even L, half the length of the solenoid, or 2L, the length of the solenoid. Then in that case what happens is that this R minus x square plus A square, okay, raised to the power of 3 by 2, this I can ignore, and x I can ignore in comparison to R, so this turns out to be equal to R raised to the power of 3, right sir? R raised to the power of 3, and our life is safe. Okay, so now the value of B I can write as mu naught nia square upon 2r cube between the limits minus L and L dx. That's easy. The integral will turn out to be equal to x, and L minus minus L become equal to 2L. Okay. Now what I do is I multiply, I bring in with mu naught the pair mu naught upon 4 pi. So I have here nia square upon r cube into 4 pi L. Okay, 2 pi I multiply here and 2 pi I multiply. Okay. Now the magnetic dipole moment is equal to n into 2L, the length, number of turns into 2L, that is the total number, pi a square. Okay, pi a square, right, nia square, that will be there. So if I substitute this in this equation, what I am going to get is mu naught upon 4 pi 2m upon r cube. Okay. Here I have shown just the needle, which is a compass needle making an angle theta with the magnetic field, any magnetic field under consideration, and this is the uniform magnetic field, so it's there. What I get is mu naught upon 4 pi 2m upon r cube, and this is the long side arm, this is on the axis of it. And if you remember, then we have, in the case of a dipole, electric dipole, 1 upon 4 pi epsilon naught, here 2p upon r cube. Okay. So there is a similarity with that one also, and this is the result which we obtained for the bar magnet, and we have got the result for the equivalent solenoid. So a bar magnet or a solenoid may act like each other. Okay. We return with more, okay, in the next lecture. So thus far, this is I could do it because I knew the results. You cannot immediately write this. You have to scribble the things, okay, and finally write it over here. You can, of course, like what you do is that you remember the end result, okay, but always remember that this is the magnetic field. It depends upon the dipole moment vector and also inversely proportional to r cube. So I hope that if you put a little bit of labor into it, then you are intelligent enough to arrive at this result and know how to arrive at this result. You can make your own shortcut, if any, but I think the long cuts are always better for bright students like you in learning stage. Thank you very much. Okay, and I still have kept this thing. You question, we answer, which I am expecting from you to put up questions and indicate to me if I have done anything wrong, so that I make corrections. Okay, thank you very much. See you again.